Hi there, my name is Miranda Maynard, and I'm making a presentation for Data Mining and Machine Learning DA 5030. My project is called Classification of Chronic Kidney Disease, so let's jump right in. I'll first talk about where this data set comes from. So this data set is about chronic kidney disease, and I got it from the UCI Machine Learning website, so we can go visit that real quick. You can see it has the data folder for downloading, some information statistics on this data set. It is real data that came from hospitals in India, and it has some feature information. Going back to the project here, the goal of this project was to see if it was possible to classify whether a patient has chronic kidney disease or not, given some various features, mostly coming from health tests, so things like urinalysis and blood tests. That's where most of these features appear to be coming from, and see whether we can build a classification model from these that can say whether the patient has chronic kidney disease or not, and how accurately we can create a model from that. So moving forward, I got the data via CSV. We can read it into our environment, and let me just show here. So this is the R Markdown for this particular project. I am going to have this running in the background so we can just show that all of this code is running nicely. And then let's go back to the presentation here. So one of the first things that I wanted to do is take a peek at all the features and what the distribution of the features were. So we can see here I did a histogram for every numerical feature. Appeared as though we were having outliers. I also did a box plot to see if what we were truly seeing appeared to be some sort of outliers. So I'll use blood pressure here as one of the features. It appeared to have some outliers up here around 180. So I did a little bit of a box plot, and sure enough, these values are sort of outside of the quantile range. I decided to actually keep in all of the outliers for this data, and my reasoning was that I don't believe they're outliers. I think they're extreme values based on patients that have other underlying diseases, so in this case of blood pressure. One of the other features in this data set is whether the patient has hypertension or not, and more often than not, some of these values correlated to patients that had said, yes, they have hypertension. So most likely we're seeing high blood pressure because of those patients, and some of them have more extreme status than others. So just going through, you can get a sense of this data. Most were right skewed, but we did histograms for this. And then we also did a pairs panel here, so we can see what some of the correlations and collinearities were between our given features. Most were, middle range, maybe like 0.3, negative 0.3. Some of them were much lower. We do have a few that are really highly correlated, so mostly between the different features that are relating to the blood, so red blood cell count, hemoglobin, white blood cell count, etc. So I decided to take a closer look at that, and you can see here we do indeed have some correlation happening between hemoglobin and the percent cell volume, packed cell volume, and these are both blood-related things. So I decided not to do PCA for the small data set. I wanted to keep most everything in there and see how our models would perform. Going back and doing this again, I would look at our features a little more closely with the principal components analysis. For data preparation, so here I looked at how much data was missing from the set. So I got the percentage of each column that had data missing. The highest amount was 38%, so some of them have a significant amount of data missing. Important to note, all of them had at least some data missing, except for our classification column, so whether the patient had CKD or not. So one of the things that I wanted to do was to impute these values, and so I decided to use an all-in-one package. I decided to use the MICE package because it's really straightforward. The only thing is I made sure to exclude our binary classifier that we were trying to predict, because you don't want to fit the data based on the classifier that you're eventually going to predict. So I excluded that when we were doing our imputation. And we can take a peek here. We did imputed values and also the original data set, so you can see there's no NAs anymore. Moving on to normalizing the data. So I used z-score normalization, and we also took a closer look at some of the outliers. So I was looking at values once we z-score normalized the numerical features. I looked at which features were greater than 3, and some features didn't have outliers and others had quite a few. So we can see here blood glucose random. We're typically going to see fairly high blood glucose random numbers when a patient has something like diabetes. Maybe it's uncontrolled or unmanaged. They may have extreme values of blood glucose. And so these outliers, again, seem to confirm my hunch is, in that these are actually real values. They're just extreme because of patients' underlying conditions. So we're going to keep those in. And that's part of the reason why we use z-score normalizing, is because I didn't want to squash the data, since we were leaving some of those outliers in, and some of those outliers would cause the values to get squashed closer to 0 if we had done something like min-max normalization. So then I dummy coded all of the categorical features. Since we're going to be doing KNN, you need to have things all normalized and dummy coded. For modeling here, I chose 4 models. I chose the KNN, C5.0 decision tree, logistic regression, and SVM models. And I chose these because they seem to be a pretty diverse group of models. We can kind of see how this data is working with each one, because each has sort of an underlying way that they are finding and classifying data. So KNN is using distance measures, decision trees is using kind of logical yes-no statements. Logistic regression, of course, is a regression model, and SVM is sort of our black box model to kind of see how they're doing toe-to-toe against each other. So let's jump over to actually the R markdown here. And what I'm going to do is I'm going to run this. You can see it ran. Everything worked out nicely and is working properly. But let's jump down here to our modeling section so I can show you some of that. So if we go to modeling here, I'm just going to run this as we go along. We have KNN. I just set up everything with default features. So using the square root of the data set to find K, I just did K equals 17 on our first pass through. And I am using accuracy measures as well as AUC to evaluate these models and see how well they do against each other. So, first pass through using default features for all of these. An interesting little side note, the decision tree model had 100% usage of the hemoglobin feature, so most likely hemoglobin is playing a pretty big part in making the decisions for our CKD. And so then going down here, we can see a confusion matrix for each one so that we can get our 95% confidence interval and how well each one's working. So if we go down here, I actually list out next to each other what all of the accuracies were. So we can see KNN with just default quick features is working the least well. Decision tree is tied with actually logistic regression as working next best, and then SVM is actually working quite well. Our numbers here, I'm hesitant because we did so much imputation of this data, we may be having a case of overfitting, and so our model is actually working better than expected. In a real life situation, we would want a data set that doesn't have so many missing values that we could use to do all of this. So then I decided to tune the models. I just used the caret package and the train function from the caret package, because what it'll do is it will take a method and go out and find the best features, the best parameters for that model. And when we did that, we found an improvement for each model. So KNN was around like 96. The decision tree and the SVM models were actually working pretty toe-to-toe around 99. And the logistic regression was somewhere above the KNN but below the decision tree and SVM. So it seemed like those tuning measures worked really well and everything was working fairly well. So a stacked ensemble model, maybe it would improve accuracy, so we just forged forth and tried anyway. I built the model using the metadata from KNN, the CO5 decision tree, and the SVM. Those are the 3 base models that I used for this stacked ensemble. You get the predictions for each one of those at their optimal settings, and then save those predictions as a column in our training data set. and then use only those 3 columns. We have a top method that we're using to calculate, to do our overall model, so we're stacking here. And the overall method that I used was actually logistic regression, so I used all 4 of the ones that I had been testing in the regular section here. So then once we get that all working for training data, we set it up for the testing data to really test it and see how well it's doing. And our overall model ensemble here is working at about the best as our best equation, our best models were. So our SVM and our decision tree, we're getting a pretty good interval here. I'm hesitant to say that this is working quite as well as it seems to be. So let me run this all again while I am explaining this. But it seems as though we may be having overfitting happening, and that's why we're getting some of these really nice prediction numbers. Certainly when it comes to the health field, you want very confident predictions, and you want really accurate predictions, because someone's life is honestly being influenced by these decisions. So I think for deployment and for confidence sake, we would really want a whole and complete data set to be running all of these on, so something that we didn't have to impute a bunch of values for, and certainly more data. We only had 400 cases in this particular data set. If we were to do the same process over again and be seeing some good numbers with that, then we could feel a little bit more confident about potentially moving towards a deployment of such a model. But certainly we would really want to feel confident before doing so. And right now I don't feel super confident. We did a lot of imputation, so we may be having some sort of artificial results. So we'll just let our data finish up running here, and I want to say, thank you for tuning in and listening, and I hope that this was a good presentation. Happy holidays, and thank you for a great semester. Goodbye.